Okay, so thank you so much to come to this new new webinar for this Red Latinoamericana de Físico-Química Teórica. So today, Said Jalife will give the lecture, the webinar. And Said was a member of our group for many years, almost 8 years, because he started as a bachelor in Guanajuato. And later on, he moved to Merida and started the master thesis with me. And finally, he obtained the PhD 2 years ago. And the thesis was really interesting because he studied some fluxional systems, carbocations, and also some boron clusters that has this interesting property. Later on, he makes some interesting work in some area that is totally different, that it's related with some areas of politicians, and try to promoting science in Mexico. And finally, 1 year ago, around, he joined to the Department of Chemistry in University of Oxford with Professor Fernanda Duarte. And right now, he is almost member of the group of Professor Judy Wu in Houston. And today he will speak about new insight into the Fritsch-Buttenburg-Wiechell rearrangement. Okay, Said, thank you very much for accepting the invitation, and please.
Yeah, so thank you for the introduction. And well, today I'll be talking about the Fritsch-Buttenburg-Wiechell rearrangement. This is a really old reaction, but it has some interesting mechanistic questions, as well as some modern applications and examples. So, this reaction was originally published in 1994. This reaction was originally proposed as a reaction involving a diaryl halide compound, which under high temperatures and toxic bases formed by alpha elimination reaction, vinylidene carbene type structure, in this case 2, and then by the migration of any of the two substituents, you form the corresponding diaryl acetylene compound. So this hypothesis was challenged by Butner-Bai, Corin coverage during the 60s in a series of labeling carbon experiments, showing that the antiperiplanar migration of the beta substituent groups relative to the halogen migrate in a stereoselective way. So by this, they actually rule out the formation of a symmetric vinylidene carbene. Otherwise, they would expect a different or more similar yields of these reactions. So in this case, you can see with a red point the labeling carbon, and whether you start from the Z or E isomer, in their experiments, you always get a preferential migration of the group anti to the halide atom. So in this case, in the Butner-Bai experiment, you can see that phenyl group is actually migrating with higher yields. And from the E isomer, you have the substituted phenyl group migrating preferentially over the phenyl group. So in this case, the anti-migration is preferred. Similarly, in the coring and coverage experiments, you obtain similar results in which they only change the reaction conditions. Actually, these are the most common conditions nowadays to obtain this type of rearrangement. So basically, you have the same vinyl halide compounds. You employ low temperatures organolithium compounds, and whether you can employ polar or non-polar solvents, you will see that these stereoselective results are preserved, right, in both of the cases. So this has led to the following debate about this, the FBW rearrangement, in which some people think that the reaction proceeds via an alpha elimination, forming the vinylidene carbene type structures. And others point out that the reaction actually proceeds via a direct rearrangement from a carbenoid species. So this carbenoid species is actually formed by the reaction of the vinyl halide with organolithium compounds, and you form this type of carbenoids, where M is electropositive metal, usually lithium, and X is an halogen. So you can actually see if this is chloride or bromide usually. So this is like one of the big questions, but I'm going to focus more on the below reaction. So more modern examples of this FBW rearrangement can be found forming a long chain of acetylene units. And also you can form biologically active natural products. There are also reports on surface using atomic manipulations to obtain this type of acetylene compounds. Or you can actually have more complex P-conjugated systems, materials. During the 80s, Walborski actually reported the reactions of chiral carbenoids and studied his stereochemistry and mechanism. So treatment of this vinyl halide compound using terbutyl lithium and subsequently using deuterolysis reactions, you obtain first the corresponding carbenoid by a hydrogen lithium exchange reaction. And then if this type of carbenoids can be attacked by a nucleophile, in this process, what you will see is the direct nucleophilic attack trans to the living halogen with the simultaneous ionization of the carbon halide bond, forming a tight ion pair structure and placing the positive charge on an NTP orbital. This reaction forms the corresponding product with inverted configuration. So this means that the nucleophile attack in a specific phase of the carbenoid and anti to the alive atom. This hypothesis can be applied to the FBW rearrangement, in which the beta substituent group anti to the halogen atom perform a nucleophilic attack towards the alpha carbon, form the corresponding cationic intermediate with the tight ion pair and an MMTP orbital at the alpha carbon, and then forming the corresponding acetylene compound. So we decided to analyze a series of prototopic carbenoids, vinylidene carbenoids, using different substituents. We decide to employ for R1 and R2 methyl groups, alkenyl groups or vinyl, alkenyl and phenyl groups. So in total, these are 16 species using lithium and chloride as expelled atoms. So in the case of the antiperiplanar migration of these prototype carbenoids, we found that the antiperiplanar reaction proceeds in most of the cases via a concerted mechanism in which you will find or you will form a vinylidene carbene type structure in which a lone pair and an empty p orbital is located at the alpha carbon. And the reaction proceeds with the simultaneous migration of R1 group and the ionization of the chloride and carbon bond in order to form the corresponding acetylene. And we also found that in some cases you can have a stepwise migration in the cases where the non-migrating R2 or stationary group is a phenyl or vinyl group. In this case, the reaction involves is a two-step process involving this intermediate in which the p orbital is actually located at the beta carbon, and the R1 group is fully migrated to the to the carbon alpha atom, right? So on the other hand, the symperiplanar migration from these carbenoids proceeds mainly by a stepwise mechanism. And this is likely due to the presence of the chloride in one of the enantiomer phases that hinders the migration of the R2 group. In this case, the first step involves the formation of two intermediates, one in which the chloride attacks the p-migrating groups, forming a three-membered ring, and the other where a carbene type structure is formed as an intermediate. This is the first step, and the second step actually dehalogenation proceeds with the formation of in most of the cases of the p empty orbital at the beta carbon and the migration of the R2 group at the alpha carbon. And in most of the cases, and in some cases, you will have some alkene type transition state structures. So, but what about the migration of the substituent groups? What factors are playing to stabilize the transition state structures? So, if we analyze the antiperiplanar migration in the first step on the antiperiplanar migration, we have different operating electronic factors here operating. So the first one is that the There's an open phase for the attack of the R1 group to the alpha carbon. And since this is an open phase, we see actually that there are strong interactions, donor, in this case I'm showing you the donor receptor NGO orbitals, where the stabilization of this deficient carbon is stabilized by hyperconjugation interactions from the migrating carbon-carbon bonds. But also there might be playing an important role conjugation interaction from the p migrating orbitals, or from hyperconjugation from the carbon-hydrogen bonds in the case of the methyl group. Actually, this figure shows the activation energies for this step, where we have fixed the stationary non-migrating group and changed the migrating group. And what we can actually see is that the barriers decrease in general, going from methyl to phenyl group. So this means that in agreement with the stereoelectronic interactions, that there are stronger conjugation interactions from the p migrating groups than the groups that has hydrogen atoms, than the hyperconjugation from the carbon-hydrogen atoms. And in the case of the simple planar migration step, as shown here, although we have the formation of a carbene type structure, the stereoelectronic interaction are relatively much weaker, and this is likely because of the presence of the chloride. This is a block and antiphase. So in this figure, we have also fixed the stationary groups, stationary non-migrating R1 groups. And then we have changed the migrating R2 group. And what we can see, and this is also in agreement with some experimental indications, that this reaction actually is more in agreement, that the barriers are in agreement with the electron withdrawal or electron donor ability of the substituent groups. Actually, we can see here that the alkene group shows the higher barriers in all the cases, and then drops for the vinyl or phenyl, which can be quite competitive in some cases. We need here to consider that these barriers also include some conformational changes. And lower barriers are shown for the methyl group, which has a more electron donor character. In this case, where we have two methyl groups, the barrier here shown is higher because this is this carbenoid shows a concerted pathway. It's not a stepwise two-step reaction. So this is why we can say this carbenoid is out of this trend. So in the second step, where we have formed the intermediates, and then we have this second transition state structures, which is quite interesting because now the p empty orbital is located at the beta carbon. So with this, it seems that the neighboring non-migrating stationary R1 group shows more evident effect on the stabilization of this reaction. And it also agrees in this case with the electron, with the nature of the beta substituent groups. As we can see here, as we fix the migrating group, and change the stationary groups, we can see that the reaction decrease going from substituent with more electron withdrawing to less electron withdrawing in most of the cases. What is quite also interesting is that in the cases where the migrating group is methyl, we would expect lower barriers, right? Because this has a more electron donating nature. But if we look at the NCI non-covalent, if we look at the NCI non-covalent interaction, we can actually see that in this step, in some cases, the methyl group is not fully migrated, and due to the hybridization of the beta carbon, the stationary group tends to linearize. So there might be some steric repulsions playing in here, while in other cases, in other cases we don't see, we don't have this type of aesthetic repulsions. Rather, we just see the NCI just reveals the attractive character of the lithium and chloride, and the lithium and the lone pair of the carbon-carbon atom. We have also realized in experiments that the FBW rearrangement can be drastically affected by a solvent, by the type of solvent. In this case, for instance, by employing a non-coordinated and non-polar solvents, we actually see that the reaction can be, that the FBW rearrangement can be promoted. While if we use polar and coordinated solvents such as tetrahydrofuran, we'll see that there are actually some dimerization reactions. Instead, from the same isomers, from the same vinyl halide compound, if we use solvent such as hexane, we will see the FBW rearrangement instead of this dimerization product. So I will just give you one example from the solvent effects. So in this case, we analyze this carbenoid where we have two methyl groups. We actually see that as we increase explicitly the number of tetrahydrofuran molecules, we see an increase in the barriers of almost 4 kilocalories per mole. These molecules are placed coordinated to the lithium atom. And the same happens with the same periplanar pathway of the methyl group. If we start by adding this type of molecule, then the barriers will increase. In this case, we see that by including implicit solvents such as benzene, the barriers can actually drop to almost 10 kilocalories per mole, 4 kilocalories. So this is kind of in agreement with what we know from experiments, right? Also, we need to consider that that this dimerization process will depend also on the lifetimes of the carbenoid, the concentration, and even the temperature employed in the experiments. But for now, what we can see is that the barriers actually increase by adding this type of or the FBW rearrangement is deaccelerated by adding these coordinated polar molecules, right? So so we can extract from now that the FBW rearrangement actually matches with the metal-assisted ionization mechanism proposed for chiral carbenoids, and that the mechanism will depend whether the beta substituent groups migrate from the open or from a block enantiophase. Also, we have learned that the stereoelectronic interactions might play an important role during the migration of the antiperiplanar, while in the case of the symperiplanar, these interactions are almost absent, and the nature of the substituent groups seems to match better with the description of the barriers. And also the solvent effects can affect drastically the barriers and can promote or prevent the FBW rearrangement. So yeah, I wanna say special thanks to Professor Fernanda Duarte for giving me the opportunity to develop this product, and also one of her, this is Professor Duarte, also one of her PhD students, Alistair, which has helped with a lot of discussion on the project. All the Duarte groups, also the Oxford University for giving me all the facilities to undertake the computational work, and CONACYT as well for the scholarship of the postdoc. And all of you for your attention.
Thank you, Said. Now we will move on to the question session. We have 15 minutes. If you have a question, first click in participants, and within there is a raise hand button. Please click this option and then I will let you know when it's your turn to ask. Another way is to let us know through the chat that you want to ask a question. Finally, people who is watching us on YouTube is also able to ask questions through the chat box. So let's start. And Gabe Gomez has a question.
Hi, Said. Thanks for the talk. And I must say that indeed, this is a very cool and weird reaction. And I think you were able to explore it deeply. So I have a few technical and not so technical questions. So like in slide 10, you showed some what you called hyperconjugative interactions that had really high magnitudes for what one would expect from natural bond orbital analysis. In fact, I would expect them to be much more in line to actual covalent bonds. 158 and 190 kilocalories per mole, in my book, covalent bonds. So do you think, what do you think about this? And is this in the transition state?
Yes, it is. That's why we are looking at those values. Yes.
Right. So still, in this case, maybe you could try to, I don't know which version of NBO you use. Do you?
It's version 7.
Wow. Okay. Even more surprising then.
Yes.
Perhaps you could try to do one of the options that you have in NBO to switch the Lewis structure, because this might not be, even looking at these orbitals, to me, they look much more like, almost like banana bonds in a way. They are not as bent, but like almost there, right? And looking into transition states with NBO is always very tricky. Yes. So I know that it's hard, which leads me to slide 12 that you showed. Here. So on the bottom left structures that you have, you even commented on the fact that the methyl group is not properly migrated, right? Like it's in between, which that's what it seems to be here.
Yeah.
And you do have a little bit of repulsive interactions there, and some van der Waals interactions. But more importantly in my book is that it seems to me that you would have a CH hyperconjugation interaction. Let me see if I can annotate. Yes, I can. So it's basically you're showing that you're donating from this CH to what is this p orbital, I would say. That's the empty. So that is odd. And I wonder if you try to verify the confirmation where you rotate this 90 degrees, where then you would have the pi system of this allo group here donating to that p orbital. But great talk. I had a lot of fun. Thank you so much.
Yeah. Thank you for your comments. It's like actually, yes, I have similar thoughts on this. I know especially you have worked a lot with this type of stereoelectronic effects. So I appreciate very much your comments.
Right. But did you look into rotating this particular
No,
a little bit?
not that one. So what could happen? Well, I can actually try to do it manually, but yes. So what? Yeah, I need to look at the. Yeah, no, I haven't done it, but I think that I can try to rotate it and see how these interactions play with the MTP orbital there. We can also have another transition structure there where this vinyl group is not on the skeletal plane of the carbon-carbon, but instead it's out of this plane and pointing up or opposite to the methyl group. But yes, I haven't done that. But what I remember is that most of the interactions comes from the migrating group rather than the stationary group.
It can be like a remote control, and because here what we look at, it's like, this looks like conjugation, okay, and we'll try to be plain. But you can have selective transition state interactions that might in fact be taking a role here, especially because of this steric clash that you have in the like basically a 1,3 allylic string. I don't know, but it's very cool.
Yeah, I will definitely look at this just to see the influence of this vinyl group here in these transition structures.
Okay, now it's the turn of Professor Gabriel Merino.
Very nice talk, Said. I have a question related to the aggregation. So as you know, lithium, it's a metal that it's prone to form aggregates, even in solution. But so, for example, the material lithium in solution forms polymers. However, here you didn't consider that. So you only take one molecule and you don't consider that perhaps it's possible to form such polymers or such aggregates. And this aggregation could change the reaction, no? So perhaps the transition state will be totally different, or at least the barriers could be lower or higher, depends on the environment. So why you didn't consider that?
Yes. Well, I think also, well, in some experiments, you have these polar solvents that are expected to be coordinated to the lithium atom, right? So in that sense, you will prevent other molecules to form this type of dimers yeah, this type of polymers. Also, yeah, I'm just to the top of my head, I'm just thinking that I wouldn't sure how will that affect the rearrangement, because what we have seen and known about this rearrangement is that the migration of the beta substituent groups comes with the simultaneous migration of the chloride atom, right? So I'm not sure if forming this type of dimers or polymers will actually help or prevent this rearrangement. Although it might be good to see whether in a dimer I will first it's whether this dimer is thermodynamically more stable or if the reaction proceeds in the same way. Maybe we will observe a different mechanism, but that would be the two reasons: the solvent and that yeah, maybe it's a good idea to explore the dimers of this type of structures. Also,
Yeah.
I'm not sure about the concentration, how will also affect this type of polymerization.
Yeah. I agree that perhaps the solvent will prevent some polymerization, but at the same time, so these solvents will play an important role. But you also consider such solvents in the reaction. So perhaps only you consider that as a field. So put intrinsically the solvent, but not explicitly. So I think this could be also important. No? So to check the polymerization and also check the explicit solvent molecules around the clusters. Okay, thank you, Said. Nice talk.
Is there any other question? No, well, so one more time, we thank our speaker, Dr. Said Jalife, and the entire audience for joining us today. Remember that we will have a webinar in 2 weeks. The next one will be given by Jose Manuel Guevara from UNAM, Mexico. All the information will be available in our social networks. See you soon, and thank you all again.
Gracias,
Thank
Said.
you, Said.
Thank you.
Ya dejamos de grabar, ya.